For more than a decade, we have been told the universe is about 13.8 billion years old. But the James Webb Space Telescope is seeing galaxies that appear far too massive, far too bright, and far too mature for how early they existed. These discoveries are forcing astronomers to look again at what they thought they understood about the beginning of everything. So what exactly has Webb found? And could the universe be older than we think? Before we begin, like the video, subscribe to the channel, and turn on notifications for more journeys into the deepest mysteries of space. At the outermost reach of the observable universe, distance and time become almost the same measure. Light travels at a finite speed, so every distant object appears as it was when its light began the journey toward the present. Nearby stars appear only a few years or a few centuries in the past, while distant galaxies appear millions or billions of years earlier. At the farthest visible limits, the light begins its path when the universe is still very young. This boundary is not a wall in space. It is a horizon set by the age of the cosmos, the speed of light, and the expansion of space between widely separated regions. The observable universe is the region from which light or other signals have had enough time to reach the present location since the early cosmic expansion began. The whole universe may extend far beyond this region, perhaps without any known edge, but observations can only describe the part within the cosmic horizon. Because space expands while light is travelling, the present distance to the most remote observable matter is much greater than the distance light would cross during 13.8 billion years in an unchanging universe. The oldest visible regions are now separated by tens of billions of light years in present-day distance, even though their light has travelled for a shorter span of cosmic time. This distinction between travel time and present distance is essential. Light does not move through a fixed background while the universe remains still. The space through which it passes stretches along the way. A wave of light lengthens as space expands, shifting toward redder wavelengths. This effect is called cosmological redshift. It arises because the space between a distant galaxy and the observer grows while the light is in transit. Greater redshift generally indicates that the light begins its journey earlier, when the universe is smaller and denser. At the visible frontier, galaxies become faint, compact, and strongly redshifted. Their original ultraviolet and visible light arrives in the infrared, where instruments designed for cold and distant targets can detect it. The James Webb Space Telescope observes this stretched light with a large segmented mirror and sensitive infrared instruments. It does not look beyond the beginning of the universe, and it does not see the moment of the Big Bang. It studies later light from stars, gas dust, and galaxies formed during early cosmic history. Its deepest images extend the known record of luminous objects closer to the cosmic beginning without reaching the beginning itself. The edge of the observable universe changes with time. As cosmic time passes, light from more distant regions can arrive, bringing new areas into view. At the same time, accelerated expansion increases the separation between remote regions. Some places that can be observed now may emit new light that never reaches the far future, because the intervening space expands too rapidly. The observable horizon is not a sphere with a permanent material surface. It is a changing limit shaped by the history of expansion. The age near 13.8 billion years does not come from measuring a single oldest galaxy. It emerges from observations that describe how the universe expands and what it contains. Measurements of ancient background radiation, the distribution of galaxies, the abundances of light elements, and the present expansion rate contribute to a consistent cosmic history. Within the standard cosmological model, these observations allow researchers to calculate the time since the hot, dense early state. The result has a limited uncertainty, but it does not depend on one telescope. Distant galaxies provide a different kind of evidence. Their light reveals how much structure exists at specific stages of cosmic time. Once a redshift is measured, a cosmological model converts that redshift into an estimated look-back time and an age of the universe at emission. A galaxy seen at very high redshift may appear as it exists only a few 100 million years after the early expansion begins. Its stars may already contain heavy elements, its gas may be forming new stars rapidly, and its total light may be brighter than earlier models predict. Such findings can challenge ideas about how quickly galaxies assemble, without directly proving that the universe is older than the age inferred from broader cosmological evidence. The phrase observable universe also carries a limitation. Astronomy depends on light that survives a long journey through changing space. Some of that light is absorbed by gas scattered by dust, or shifted outside an instrument's range. Some sources are magnified by the gravity of nearer galaxies, while others remain too faint to detect. Every deep image is therefore selective. It contains objects bright enough and favourably placed enough to be measured. The absence of an object does not always mean that no object exists, and an unexpectedly bright source does not immediately reveal its true mass or age. At this outer scale, the universe appears statistically uniform across very large distances. Galaxies gather into groups, clusters, filaments, and broad walls around immense regions. With fewer galaxies, yet no known location occupies a central position in the expansion. The observable sphere is centered on the observer only because light is collected from that position. An observer in another distant galaxy would describe a different observable sphere centered there. Each horizon reflects a location in space-time rather than a privileged center of all existence. The most distant light carries two connected stories. One concerns the objects that emit it, including their stars, gas dust, and central black holes. The other concerns the path the light follows through an expanding cosmos. Webb measures the first through brightness, color, shape, and spectrum, while cosmology supplies the framework that connects redshift with time. When an early galaxy appears unexpectedly developed, the tension lies between the observed object and models of rapid structure formation. The cosmic horizon remains the broad boundary within which that tension is interpreted. At the edge of observation, certainty becomes careful rather than absolute. The age of the universe remains close to 13.8 billion years, under the standard model supported by several independent lines of evidence. Webb adds sharper information about early luminous matter, not a direct clock placed at the beginning of time. Its observations may require changes in assumptions about star formation, dust, black holes, or galaxy growth. They may also refine parts of cosmology as measurements improve. At this outermost region, the evidence defines the scale of the problem with restraint. The horizon marks how far light can carry knowledge, and every claim about cosmic age begins within that limit. Beyond the first generations of galaxies lies an older layer of evidence not farther away in any simple spatial sense, but earlier in cosmic time. It appears as a nearly uniform glow spread across the entire sky. This radiation is called the cosmic microwave background. It is the oldest light that travels freely through space and reaches modern instruments. Its faint pattern records the universe when it is about 380,000 years old, long before stars and galaxies take recognizable form. In the earlier stages, the universe is hot, dense, and filled with rapidly moving particles. Light cannot travel far because free electrons repeatedly scatter photons, the particles of light. Matter and radiation remain closely linked in a bright, opaque plasma. A plasma is a gas in which electrons are separated from atomic nuclei. The young universe in this state resembles a glowing fog, although it has no surface and extends through all space. Expansion steadily cools this plasma. As the temperature falls, electrons move slowly enough to join with positively charged nuclei. Most of these nuclei are hydrogen and helium. The formation of neutral atoms greatly reduces the scattering of light. Photons that had been trapped among charged particles begin to move freely across the expanding universe. This transition is known as recombination, the first stable joining of electrons and nuclei. The released light forms the cosmic microwave background. At the time of its release, this radiation is much hotter and its wavelengths are much shorter than they are now. Cosmic expansion stretches the light during its long journey. Over billions of years, the wavelengths lengthen into the microwave part of the electromagnetic spectrum. The radiation now has a temperature of about 2.7 degrees above absolute zero. It remains in every direction as a remnant of the hot state. The background is extremely smooth, but it is not perfectly uniform. Tiny temperature differences appear across the sky. These variations are only a few parts in 100,000, yet they preserve information about slight differences in density. Regions with a little more matter exert slightly stronger gravity. Over long periods, these small imbalances grow as matter gathers into larger structures. The later network of galaxies and clusters develops from these early variations. Space missions measure these patterns with increasing precision. Instruments separate the ancient signal from microwave emission produced by the Milky Way interstellar dust and distant radio sources. After this foreground material is removed, the remaining map shows subtle warm and cool patches. The size, spacing, and strength of these patches depend on the contents and geometry of the universe. They act as evidence for ordinary matter, dark energy, and the overall expansion history. Before neutral atoms form, sound waves move through the hot plasma. Gravity pulls matter inward, while radiation pressure pushes outward. These competing effects create repeated compressions and expansions. Their traces remain in the temperature pattern of the cosmic microwave background. Researchers study the statistical distribution of these traces rather than interpreting each patch as an isolated object. The pattern forms a record of conditions across the young universe. The angular size of the strongest features helps reveal the geometry of space. In a strongly curved universe, the apparent scale of these features would differ from the scale measured in a nearly flat universe. Observations indicate that space is very close to geometrically flat on large scales. Local gravity still bends space-time around stars, galaxies, and clusters, while the large-scale geometry remains close to the flat case. The relative strength of the background patterns also constrains the density of matter. Ordinary matter includes atoms, gas dust stars, and planets. Dark matter does not emit light, but its gravity affects the growth of cosmic structure. The measured pattern indicates that dark matter is substantially more abundant than ordinary matter. The remaining large contribution in the standard model comes from dark energy, the component associated with accelerated expansion at later times. Once these quantities are estimated, the equations of the standard cosmological model describe how the expansion rate changes. The model can then calculate the elapsed time between the early hot state and the present. This calculation produces an age close to 13.8 billion years. The result is not simply the travel time of the background photons. It depends on the expansion history, which changes as radiation matter and dark energy dominate at different stages. The age derived from the cosmic microwave background is model-dependent, but it is not arbitrary. The model must reproduce many measured features at once. A different cosmic age would alter the expected pattern unless other quantities changed together. Alternative models must also remain consistent with galaxy distributions, light element abundances, gravitational lensing stellar ages, and nearby expansion measurements. Most changes struggle to match the full set of observations as successfully as the standard model. The cosmic microwave background also contains polarization, a preferred orientation in the vibration of light. This pattern forms through scattering in the early plasma and later interactions with ionized gas. Polarization provides additional constraints on early density variations and later ionization. It also helps test inflation, a proposed period of extremely rapid early expansion, though the physical cause remains uncertain. The background does not reveal the first instant. Before the universe becomes transparent, light cannot move freely enough to provide a direct image. The cosmic microwave background is therefore a boundary of electromagnetic observation. It shows the surface of last scattering, the broad era when photons stop interacting frequently with free electrons. Every direction reaches a different part of that ancient layer, producing a shell of early light around the present observer. James Webb does not replace this record. Its infrared instruments study objects that form much later after gravity turns small density differences into stars and galaxies. The microwave background establishes the large-scale conditions and cosmic timeline within which those objects develop. When Webb finds galaxies that grow faster than expected, researchers first examine models of star formation and structure growth. The age supported by the background remains a separate and more deeply anchored measurement. At this early layer, the universe is not yet filled with visible stars. It is a cooling sea of neutral atoms, dark matter, and fading radiation. The microwave glow preserves the final stage when matter and light remain closely connected. Its delicate variations contain the seeds of later structure, while its overall temperature records the stretching of space. From this ancient light, cosmology gains one of its clearest clocks, built not from a single object, but from the measured state of the whole observable universe. After the cosmic microwave background is released, the universe enters a long interval without stars. Light from the earlier hot plasma continues to travel through space, but no new visible sources yet shine. Matter is mostly hydrogen and helium, with a very small amount of lithium, while dark matter provides most of the gravity that shapes large structures. The temperature continues to fall as space expands, and the young cosmos becomes increasingly transparent, quiet, and dark. This interval is often called the cosmic dark ages. The name refers to the absence of stars and galaxies rather than to an absence of radiation. The microwave background remains present, though its wavelengths stretch and its energy weakens. Neutral hydrogen fills much of space, and this gas interacts with light in ways that later observations may detect. The universe is not empty. It contains matter arranged in faint variations inherited from the earlier plasma. These variations begin as tiny differences in density. Some regions contain slightly more matter than the cosmic average, while others contain slightly less. Gravity acts more strongly where matter is denser. Over time, the denser regions attract additional material. The thinner regions lose matter more easily and become broader empty spaces. This slow separation establishes the earliest pattern from which the later cosmic web develops. Dark matter plays a central role in this process. It does not absorb, reflect, or emit light, but it responds to gravity and contributes its own gravitational pull. Because dark matter does not interact strongly with radiation, it begins gathering into clumps before ordinary gas can collapse as efficiently. These clumps form broad gravitational wells. Hydrogen and helium gradually fall toward them, increasing the density of ordinary matter in the same regions. The growth remains slow at first. Cosmic expansion carries distant regions apart while gravity tries to draw nearby matter together. On very large scales, expansion continues. Within small, overdense regions, gravitational attraction gradually becomes strong enough to resist that expansion. Matter starts to collect into sheets, filaments, and rounded concentrations. The structures are still diffuse, and no stable star has formed. Neutral hydrogen dominates the ordinary matter. Each hydrogen atom contains one proton and one electron, and the lack of free electrons makes the universe far more transparent than the earlier plasma. Even so, hydrogen does not allow every wavelength to pass freely. It absorbs specific forms of ultraviolet light and interacts with radiation through a faint signal associated with a wavelength of 21 centimeters at emission. Cosmic expansion stretches this signal before it reaches modern instruments. The 21 centimeter signal arises from a small change in the energy state of neutral hydrogen. The proton and electron behave as if they possess tiny magnetic orientations. When their relative alignment changes, the atom can release or absorb a photon at a particular radio wavelength. Across immense regions, this weak process may preserve a three-dimensional record of gas temperature and density during the Dark Ages. Detecting it remains difficult because foreground radio emission is much brighter. The gas also cools as the universe expands. At first, remaining free electrons keep ordinary matter loosely connected to the background radiation through scattering. As expansion continues and the density declines, this connection weakens. The gas temperature then falls more rapidly than the temperature of the radiation. This difference affects how neutral hydrogen absorbs the background signal and helps define the physical state of the dark universe. Gravity slowly compresses gas inside dark matter concentrations. Compression raises density, but cooling is necessary for a cloud to contract substantially. Pure hydrogen and helium gas has limited ways to release heat. There are no heavy elements, dust grains, or complex molecules from earlier stars because no stars have yet created them. A small amount of molecular hydrogen can form through reactions involving residual electrons and ions. This molecule becomes an important cooling agent in the densest clouds. Molecular hydrogen allows gas to lose energy by emitting radiation during collisions and changes in molecular motion. The process remains less efficient than cooling in gas enriched with heavier elements. As a result, the first collapsing clouds tend to remain relatively warm. Higher temperatures increase internal pressure, so a large amount of gas must gather before gravity overcomes that pressure. The smallest early structures therefore do not resemble the cooler, chemically richer star-forming clouds found in later galaxies. The Dark Ages have no sharp beginning separate from recombination. They emerge gradually as the last scattering light moves freely and matter continues to cool. Their ending is also not a single event across all space. Different regions reach the conditions for collapse at different times. Some dense areas evolve more quickly, while wide low-density regions remain dark for much longer. Cosmic time is shared, but local development is uneven. Observations of this interval are indirect. No telescope can photograph ordinary Dark Age gas as a bright landscape, because the gas produces little visible light. Researchers instead examine the background radiation, the later distribution of galaxies, and possible radio absorption by neutral hydrogen. Computer simulations follow gravity gas motion chemistry and expansion from measured early conditions. These simulations show how modest density differences can grow into complex structure without requiring large initial irregularities. The duration of the Dark Ages depends on the definition used and on the location considered. The first gravitationally bound gas clouds begin forming before the universe contains widespread light. For much of the cosmos, darkness continues even after isolated dense regions begin changing. The large-scale environment remains cold neutral, and only weakly illuminated. Matter gathers silently through processes that leave few direct signals. This period does not imply that cosmic development pauses. It is an active era of accumulation. Dark matter halos grow through collapse and merging. Gas streams into their gravitational wells. Molecular reactions slowly alter the cooling ability of the densest regions. The basic ingredients remain simple, but their arrangement becomes increasingly structured. The smoothness seen in the microwave background gives way to a more uneven distribution, guided by gravity over tens of millions of years. Within this starless layer, the age of the universe is still determined by the same expansion history that governs every later observation. Nothing in the Dark Ages provides evidence for an older cosmos hidden behind the measured timeline. Instead, the interval shows how much development can occur before light from stars becomes available. It forms a quiet bridge between the transparent early universe and the first compact concentrations of ordinary matter, with every change taking place inside darkness. Within the densest parts of the dark universe, gravity continues to draw gas into growing concentrations. Hydrogen and helium fall into the centers of dark matter halos where pressure and temperature rise. The gas remains chemically simple, but molecular hydrogen allows part of its heat to escape. As cooling proceeds, the central regions contract further. Density increases, collisions become more frequent, and the first compact stellar embryos begin to form. These earlier stars are often called population 3 stars. The name refers to a theoretical generation made almost entirely from hydrogen and helium, without the heavier elements produced inside later stars. No unquestioned example survives nearby, so their properties are inferred from physical models and from the chemical patterns left in ancient stars and gas. Observations indicate that at least some are more massive than typical stars forming in the present universe, though their full mass range remains uncertain. A forming star becomes luminous when pressure and temperature in its core grow high enough for nuclear fusion. Hydrogen nuclei begin combining into helium-releasing energy. Radiation pushes outward, while gravity pulls inward, creating a temporary balance. The first starlight enters a universe that has remained without stellar illumination for tens or perhaps hundreds of millions of years, depending on the region and the definition used for the beginning of star formation. The first stars emit strongly in ultraviolet wavelengths because their surfaces are extremely hot. Ultraviolet photons carry enough energy to remove electrons from neutral hydrogen atoms. This process is called ionization. Around each young star or group of stars, a growing region of ionized gas develops. Inside such a region, hydrogen separates into free protons and electrons. Outside it, most intergalactic hydrogen remains neutral. At first, these ionized areas are small and isolated. Dense gas near a star absorbs much of the ultraviolet radiation, and free electrons can recombine with protons, returning the hydrogen to a neutral state. Continued ionization therefore requires a steady supply of energetic light. The size of each ionized bubble depends on the brightness and lifetime of its sources, the density of the surrounding gas, and the rate at which electrons and protons join again. Early stars are short-lived when they are very massive. They consume nuclear fuel rapidly and may survive only a few million years. Some end through powerful stellar explosions, while others may collapse more directly into black holes. Their deaths enrich nearby gas with carbon, oxygen, silicon, iron, and other elements heavier than helium. Astronomers refer to these elements collectively as metals, even when they are not metals in ordinary chemistry. This enrichment changes the behavior of later gas clouds. Gas containing heavier elements can cool more efficiently than pristine hydrogen and helium. It can fragment into smaller concentrations, allowing stars with a wider range of masses to form. Dust produced by early stellar explosions may add further cooling pathways. Star formation gradually shifts away from the purely metal-free conditions associated with the first generation. The transition is uneven because enriched material spreads locally, before mixing across larger distances. Small early galaxies gather multiple generations of stars within shared dark matter halos. These galaxies are faint by later standards, but together they can produce large amounts of ultraviolet radiation. Some of that radiation escapes through gaps in surrounding gas and enters intergalactic space. The fraction that escapes is difficult to measure directly at extreme distances, yet it strongly influences how rapidly neutral hydrogen becomes ionized. As the number of luminous sources increases, separate ionized bubbles expand and begin to overlap. Regions surrounding groups of galaxies merge into larger ionized zones. Reionization is therefore not a single flash across the cosmos. It is prolonged and uneven transformation. Dense areas containing many galaxies change earlier, while remote low-density regions can remain neutral for longer periods. The process unfolds across several 100 million years. Neutral hydrogen leaves a clear mark on light passing through it. It strongly absorbs radiation at wavelengths, associated with a transition called Lyman alpha. In the spectra of very distant galaxies and quasars, this absorption can reveal how much neutral gas lies along the path. When the intergalactic medium is highly neutral, much of the relevant light disappears. As ionization advances, more radiation can travel through expanding transparent regions, though dense pockets of neutral gas continue to absorb it. The cosmic microwave background also carries evidence of reionization. Newly freed electrons scatter a small fraction of the ancient background photons and alter their polarization. Measurements of this effect provide an estimate of the broad timing of the transition. These observations indicate that reionization develops gradually rather than occurring at one precise moment. They also place limits on the amount of early star formation required to free electrons across intergalactic space. Quasars provide another line of evidence. A quasar is an intensely bright region surrounding a rapidly feeding black hole at the center of a galaxy. Light from distant quasars passes through large stretches of intergalactic hydrogen. The resulting absorption pattern shows that the universe is mostly ionized by roughly 1 billion years after the beginning of expansion, while significant neutral regions remain at earlier times. The exact pace differs among locations and remains an active subject of measurement. Reionization changes the thermal state of ordinary matter between galaxies. Ultraviolet radiation heats the gas as atoms lose electrons. Warmer gas resists collapse into the smallest dark matter, halos reducing the ability of some low-mass systems to form stars. Radiation from early sources therefore influences later structure by altering the supply and temperature of gas. The first luminous objects do not simply illuminate their surroundings, they also reshape the conditions for future star formation. The stars and galaxies responsible for reionization are difficult to observe because they are distant, faint, and partly hidden by intervening hydrogen. Some detected galaxies are bright enough for detailed study, but many important contributors may lie below present detection limits. Models combine observed galaxy populations with estimates of faint unseen sources, ultraviolet production, and escape fractions. Evidence supports a major role for early galaxies, while the exact contributions of different stellar populations and feeding black holes remain uncertain. During this transformation, the universe contains sharply different environments. Ionized regions surround luminous concentrations. Neutral gas persists between them, and newly enriched material spreads through local space. The change from darkness to widespread transparency is gradual, patchy, and governed by gravity radiation, atomic physics, and stellar evolution. Rhionization marks the interval in which sustained light alters most intergalactic hydrogen, leaving the large-scale cosmos transparent to ultraviolet radiation that the earlier neutral gas absorbs. The James Webb Space Telescope reaches toward the earliest visible galaxies by collecting infrared light that has traveled across almost the entire observable history of the universe. The galaxies themselves do not remain at the distances they occupy when their light begins its journey. Space expands while the light moves, stretching every wave and increasing the separation between source and observer. A galaxy seen only a few 100 million years after the beginning now lies far beyond the distance suggested by light travel time alone. Webb records the old light rather than the present condition of the source. Webb operates near a gravitationally balanced region about 1.5 million kilometers from Earth. A large sunshield keeps its mirror and instruments cold by separating them from direct sunlight, warm parts of the spacecraft Earth and the Moon. Low temperatures are essential because warm objects produce infrared radiation. If the telescope becomes too warm, its own glow can hide the weak signals arriving from remote galaxies. The cold environment allows sensitive detectors to distinguish ancient cosmic light from nearby heat. Its primary mirror is about 6.5 meters wide and consists of 18 segments, working together as one reflecting surface. The broad mirror gathers more light than a smaller telescope during the same observing period. This ability is important because early galaxies appear extremely faint. Many release only a small stream of detectable photons after their light crosses expanding space and passes through gas dust in the optical system of the telescope. Long exposures collect these photons gradually until a measurable source appears. The earliest galaxies produce much of their detectable energy in ultraviolet light from hot young stars. Cosmic expansion stretches this radiation into near-infrared, and for some measurements, mid-infrared wavelengths. Near-infrared light lies just beyond the red end of human vision. Webb is designed to observe this range with far greater sensitivity than earlier large space telescopes. It can therefore detect radiation that begins at short wavelengths, but arrives after being stretched by more than an order of magnitude. Deep observations begin with carefully selected regions of sky. Some fields contain relatively little bright foreground dust, allowing a clearer view into distant space. Other fields include massive galaxy clusters, whose gravity bends and magnifies light from objects behind them. This natural effect is called gravitational lensing. A cluster can brighten a remote galaxy and sometimes stretch it into a narrow arc, or produce several images of the same source. The magnification allows Webb to detect objects that would otherwise remain below its sensitivity, although the lensing pattern must be modeled to recover the galaxy's true brightness. The near-infrared camera produces images through several filters, each admitting a different range of wavelengths. A distant galaxy may appear in redder filters while disappearing from bluer ones. This pattern develops because neutral hydrogen inside and around the galaxy absorbs light below a particular rest frame wavelength. Expansion moves the resulting boundary toward the infrared. Astronomers call this boundary the Lyman break. Its location provides an initial estimate of redshift and helps identify galaxies that may belong to the earliest observable periods. This first estimate is photometric, meaning that it comes from brightness measured through broad filters. Photometric selection allows large numbers of faint sources to be examined efficiently, but it can be misleading. A nearer galaxy containing dust may look unusually red. Strong emission from gas can brighten one filter and imitate the colors of a more distant source. A cool star within the Milky Way can also resemble a compact remote object. Image artifacts and detector effects require careful removal. For these reasons, an extreme redshift candidate is not automatically a confirmed early galaxy. Confirmation normally requires spectroscopy. A spectrograph separates incoming light into many narrow wavelength intervals, forming a spectrum. Webb's near-infrared spectrograph can observe multiple faint objects and locate sharp absorption boundaries or identifiable emission features. When a known feature appears at a wavelength much longer than its laboratory value, its shift provides a more secure redshift. The measurement describes how greatly cosmic expansion stretches the light between emission and observation. At the highest confirmed redshift, spectra often contain only a faint ultraviolet continuum and a strong Lyman break. Emission lines may be weak blocked by neutral gas or too faint for detection. Researchers compare independent observations' detector positions, exposure groups and reduction methods to determine whether the signal persists. Statistical confidence matters because only a small number of photons may define the result. A secure measurement must also fit the source's image colors and expected spectral shape, without requiring contradictory assumptions. Redshift does not equal distance or age by itself. A cosmological model converts the measured stretching into a time of emission. Under the standard model, galaxies with redshifts near 14 appear as they exist roughly 280 million to 300 million years after the hot beginning. Their light travels for about 13.5 billion years before reaching Webb. During that journey, continued expansion carries their present locations much farther away than 13.5 billion light-years. The telescope does not see a galaxy continuously through its history. It receives a limited packet of ancient light released during a particular interval. A deep image may combine many hours of exposure, but those hours correspond to a very small span in the galaxy's own development compared with cosmic time. Different galaxies in the same image can belong to widely separated eras because each redshift marks a different length of travel and a different stage of expansion. Webb's observations therefore build a layered view of the early cosmos. Imaging identifies faint sources through their colors and disappearance across filters. Lensing sometimes raises them above the detection threshold. Spectroscopy tests their distances by measuring displaced features in their light. Cosmology then places those measurements on a timeline. The result is not a direct view of the cosmic beginning, but a record of small luminous systems already shining within the first few 100 million years. At this depth, Webb turns stretched infrared photons into measured locations in early cosmic time, extending the visible history of galaxies toward the boundary where starlight first becomes observable. As Webb surveys the early universe, one pattern becomes difficult to ignore. Bright galaxies appear more frequently than many pre-launch calculations expect. They are found at redshifts corresponding to only a few 100 million years after the hot beginning, yet some produce enough ultraviolet light to stand out clearly in deep infrared images. The surprise does not come from the existence of galaxies at these times. Standard cosmology predicts that the first systems begin forming early. The tension comes from how many luminous objects appear and how rapidly they seem to build visible stellar populations. Astronomers describe the abundance of galaxies with a luminosity function. This statistical distribution shows how many galaxies exist at different brightness levels within a given volume of space. Faint galaxies are usually more numerous, while very bright galaxies are rarer. Before Webb begins its deepest surveys, models based on earlier observations predict a steep decline in luminous galaxies toward the earliest epochs. The available time is short, dark matter. Halos are still growing, and ordinary gas must cool, collapse, and form stars before strong ultraviolet light can emerge. Webb confirms the expected decline broadly, but it often appears less severe than some models predict. In several fields, candidate and confirmed galaxies at very high redshift are more abundant at the bright end of the distribution. The result does not mean that every survey finds the same excess, or that all early estimates remain unchanged. Small samples, uncertain redshifts, and differences in selection methods affect the exact numbers. Even so, repeated observations indicate that early luminous systems are not as rare as many simple expectations suggest. Brightness is not the same as size or total mass. A young group of hot stars can release a large amount of ultraviolet light without containing the enormous stellar population of a mature later galaxy. Ultraviolet brightness is especially sensitive to recent star formation. If a galaxy forms stars in a short, intense episode, it can temporarily appear much brighter than its average condition. A population observed during these active phases can therefore raise the measured abundance of luminous objects, even when the underlying amount of matter remains moderate. The early environment may favor uneven growth. Gas enters small halos along dense filaments of the cosmic web. Instead of arriving steadily, it may accumulate cool and trigger episodes of rapid star formation. Stellar winds and explosions then heat or remove part of the gas-reducing activity until new material arrives. This repeating pattern produces bursts. Webb preferentially detects systems caught during luminous stages, while quieter galaxies of similar mass remain below the detection threshold. Models also depend on the efficiency with which available gas becomes stars. In later galaxies, only a fraction of gas forms stars before feedback disperses or heats it. Feedback is the influence of young stars and stellar explosions on surrounding material. If early dense clouds convert gas into stars more efficiently than assumed, their galaxies can brighten quickly. The efficiency cannot rise without limit because radiation winds and explosions still act on the gas, but modest changes can strongly affect the number of detectable objects. Low abundances of heavy elements may change stellar light as well. Early stars form from gas that has experienced fewer generations of chemical enrichment. Such stars can be hotter and produce more ultraviolet radiation for a given amount of stellar mass. A galaxy with a young metal-poor population may therefore look unusually bright when interpreted through models calibrated mainly on later systems. The size of this effect depends on stellar masses, ages, and chemical composition. The measured abundance also depends on survey volume. A deep image covers a narrow region of sky, and early galaxies are not distributed perfectly evenly. They gather around the same density variations that guide the growth of the cosmic web. One field may pass through an unusually rich region, while another may contain fewer sources. This field-to-field difference is called cosmic variance. Several independent survey areas are needed before the average abundance can be estimated securely. Gravitational lensing introduces another uncertainty. A foreground cluster can magnify distant galaxies and reveal objects that would otherwise remain hidden. The same effect changes the apparent area of the background sky and depends on the mass distribution of the lens. Errors in the lens model alter the inferred intrinsic brightness and survey volume. Lensed fields provide exceptional access to faint galaxies, but their abundance measurements require careful corrections. The conversion from observed color to redshift also influences early counts. Photometric candidates can move into or out of a high redshift sample when deeper imaging or spectroscopy becomes available. Some initial candidates prove to be closer dusty galaxies or objects with strong emission features. Others receive secure confirmation at extreme distances. As measurements improve, the estimated abundance is revised rather than simply increasing. The most reliable picture combines broad imaging samples with smaller groups of spectroscopically confirmed galaxies. Even after these corrections, the bright early population remains important. It suggests that visible structure develops rapidly once suitable halos begin collecting gas. The standard cosmological framework still supplies enough dark matter concentrations for galaxies to form, but the relation between halo growth and emitted light may differ from earlier assumptions. A change in star formation efficiency, burst duration, stellar ultraviolet output or dust content can produce a large change in bright detections. Dust has a complex role. It absorbs ultraviolet light and re-emits energy at longer wavelengths, usually making a galaxy appear dimmer in Webb's near-infrared images. Very early galaxies may contain less dust because fewer stars have had time to create and distribute heavy elements. If ultraviolet light escapes with little absorption, they appear brighter than similarly active but dustier galaxies at later times. Some early systems already show evidence of dust, so the effect varies. The abundance problem is therefore not a simple conflict between one age and another. A galaxy can be unexpectedly bright, without being older than the universe that contains it. Webb measures light while theoretical models connect that light to gas stars and dark matter. When observed counts exceed a prediction, the first task is to examine that connection. The early universe may form visible galaxies more efficiently, more irregularly, or with less obscuration than expected. At this layer of the evidence, the strange result is not a broken cosmic clock. It is a young cosmos capable of producing bright islands of starlight with surprising speed. At the edge of Webb's reach, a faint point in an infrared image can suggest an extraordinary distance, but an image alone does not establish where the source belongs in cosmic history. Broad filters show how much light arrives across several wavelength ranges. They can reveal a sudden change in color that resembles the expected signature of a remote galaxy. Several nearer objects can produce similar colors, so the initial identification remains a candidate until its light is separated into a spectrum. A spectrum spreads light according to wavelength. Instead of recording a single brightness through each broad filter, a spectrograph divides the signal into narrower intervals. The result shows where radiation continues smoothly, where it falls away, and where atoms or ions add distinct features. These patterns preserve information about the source and about the material through which its light travels. For the most distant galaxies, the central measurement is the amount by which familiar features shift toward longer wavelengths. Cosmological redshift is expressed as a comparison between the wavelength observed and the wavelength produced at the source. A redshift of 14 does not mean that light travels 14 times farther than light from a redshift of 1. It means that cosmic expansion stretches a wavelength to about 15 times its original value. The relation between redshift and elapsed time is not linear because the expansion rate changes throughout cosmic history. A cosmological model is required to place the measured shift on a timeline. Hydrogen provides the strongest distance marker for many extremely early galaxies. Hot young stars emit a broad ultraviolet continuum, but neutral hydrogen absorbs photons with wavelengths shorter than a critical boundary associated with Lyman alpha. Gas within the galaxy gas near it, and intergalactic hydrogen along the path, all contribute to this loss of short wavelength light. In a spectrum, the source can appear on the red side of the boundary, and become faint or absent on the blue side. This sharp change is called the Lyman break. As redshift increases, the Lyman break moves out of visible light and deeper into the infrared. Webb's near-infrared spectrograph is designed to measure this region. It receives light through a narrow opening, a fixed slit, or a system of tiny shutters that can select many sources. Optical components then disperse the light across detectors. A low-resolution prism gathers more photons into broad spectral intervals, and is useful for extremely faint galaxies. Higher resolution settings divide the signal more finely when the source is bright enough. The observations require long exposure times because the galaxies supply few photons. Several exposures are combined while cosmic ray strikes detect a noise scattered light, and small instrumental changes are identified and reduced. The source may occupy only a narrow trace across the detector. Independent processing methods test whether the break remains in the same place and whether the faint continuum is present in repeated observations. A secure result depends on the full pattern rather than on one bright detector element. MUMS-E14 provides a current example of this method. Imaging first identifies it as a strong high redshift candidate because it appears in sufficiently red filters and drops away at shorter wavelengths. Near-spec observations then locate the spectral break at a position consistent with a redshift of 14.44. Under the standard cosmological model, the measured shift places the galaxy about 280 million years after the hot beginning. Its light travels through expanding space for roughly 13.5 billion years before reaching the telescope. The measurement does not depend on comparing the galaxy with a nearby object. It depends on atomic physics, the observed wavelength pattern, and the expansion model. Hydrogen has the same characteristic transitions wherever it is observed. When those transitions or their absorption boundaries appear at stretched wavelengths, the amount of stretching can be calculated. The physical interpretation remains subject to measurement uncertainty, but the method has a stable laboratory foundation. Some spectra contain emission lines in addition to a break. An emission line forms when atoms or ions release light at specific wavelengths. In early galaxies, possible features can arise from hydrogen, oxygen, carbon, or other elements. A set of lines with the correct relative spacing gives a particularly secure redshift, because a nearer interpretation must reproduce the entire pattern. At the highest redshifts, many useful visible light lines shift beyond the most sensitive range of the near-infrared spectrograph, while strong neutral hydrogen can suppress Lyman alpha. The continuum break may therefore carry most of the distance information. A break can still be confused with other spectral shapes when the signal is weak. Older stars in a nearer galaxy can create a broad change around a different wavelength. Dust can redden the continuum. Strong gas emission can brighten selected imaging filters and produce misleading colors. Cool stars in the Milky Way can appear as compact red points. Spectroscopy tests these alternatives by showing whether the detailed distribution of light matches a distant hydrogen break or a nearer source with another origin. Researchers assign uncertainty to the redshift by comparing models across a range of possible values. Noise can move the apparent position of the break slightly, and the absorption does not always form a perfectly vertical edge. The surrounding neutral gas can broaden the transition, while intrinsic stellar light may vary in slope. A reported redshift therefore includes a best value and an allowed range. Confirmation means that lower redshift explanations become strongly disfavored, not that every property of the galaxy becomes known with equal precision. Several galaxies near redshift 14 establish that luminous systems exist within roughly the first 300 million years. JD's GS Zisfolstein 0 measured at a redshift near 14.32 holds the distance record before MOEM Z14 receives confirmation. A second luminous source in the same early range strengthens the conclusion that the detections are not isolated instrumental accidents. Each spectrum remains individually tested, and the growing sample reduces dependence on a single field or reduction method. Spectroscopic confirmation changes the status of the evidence. A photometric candidate contributes to a probable early population, but its distance can shift when new filters or improved models are applied. A confirmed spectrum anchors the object to a measured redshift and narrows the range of cosmic times in which its light originates. At this region of the investigation, Webb's unusual result becomes firmer and more limited at the same time. The telescope confirms that bright galaxies are present very early within the established timeline, while the spectra themselves do not show that the timeline is longer. They establish where the galaxies stand inside it. A distant galaxy has no scale placed beside it and no balance that can weigh its stars directly. Webb receives only light spread across images and spectra after that light has crossed expanding space. From this signal, astronomers estimate how much stellar material the galaxy contains. The result is called stellar mass. It is not the total mass of the galaxy because dark matter gas dust and any central black hole are treated separately. Stellar mass represents the combined mass of stars and stellar remnants, inferred from the radiation that reaches the telescope. The first step is to establish the redshift. Once the distance in cosmic time is constrained, the observed brightness can be converted into an intrinsic luminosity. This conversion accounts for the spreading of light across distance and for the expansion that shifts energy into longer wavelengths. Gravitational lensing must also be included when a foreground object magnifies the source. An error in magnification can make a galaxy seem more or less luminous than it truly is, and the inferred stellar mass changes with it. Brightness alone cannot reveal mass because stars produce different amounts of light at different stages. A cluster of hot young stars can shine intensely, while containing less mass than an older population of cooler stars. Astronomers therefore estimate a mass-to-light ratio, meaning the amount of stellar mass associated with the measured amount of light. Young populations usually have a low ratio because massive stars are extremely bright. Older populations usually have a higher ratio because many luminous stars have faded or ended their lives. To estimate this ratio, researchers compare Webb observations with models of stellar populations. These models combine stars of different masses and ages and calculate the light they release at each wavelength. They also include chemical composition, because stars formed from gas with few heavy elements differ from stars formed from enriched gas. A computer adjusts the model until its predicted colours and spectrum resemble the observed galaxy. The amount of stellar material required to produce that model light becomes the mass estimate. The assumed distribution of stellar birth masses is important. This distribution is called the initial mass function. It describes how many low-mass, medium-mass, and high-mass stars form together. Low-mass stars contribute substantial mass but relatively little ultraviolet light. High-mass stars contribute enormous brightness, but survive for short periods. If an early galaxy forms a larger proportion of massive stars than the adopted distribution allows, a standard model can assign too much total mass to explain the light. Star formation history adds another uncertainty. A galaxy may form stars steadily in repeated bursts or in a rapidly rising episode. Two systems with the same present ultraviolet brightness can contain different total stellar masses if one begins forming stars recently and the other remains active for much longer. Webb observes limited wavelengths from the most distant galaxies, so several histories can reproduce similar colours. The mass estimate becomes a range rather than a single exact value. Dust changes the colours by absorbing short wavelength light and re-radiating the energy at longer wavelengths. A dusty young population can resemble an older population with little dust because both appear red. This overlap is part of an age-dust degeneracy in which different physical conditions produce similar measurements. If redness is incorrectly assigned to old stars, the model may infer a high mass-to-light ratio and an excessive stellar mass. Mid-infrared observations can reduce the ambiguity, but the faintest sources remain difficult. Glowing gas can also imitate starlight. Ultraviolet radiation from young stars ionizes nearby gas, and the gas emits strong lines when electrons return to lower energy states. These nebular emission lines can fall inside Webb's broad imaging filters. A filter may then record a large amount of light that comes from gas rather than from the smooth continuum of stars. Early analyses based mainly on photometry can interpret this extra brightness as evidence for a larger stellar population. Spectroscopy separates narrow gas features from the continuum and often lowers the inferred mass. The shape of the stellar continuum contains information about age. A noticeable change near the Balmer or 4000 angstrom region can develop when a population includes stars that are no longer extremely young. Cosmic redshift moves this feature into Webb's infrared range. A strong apparent break can suggest that star formation begins much earlier, leaving time for a substantial stellar population to accumulate. Strong emission lines or dust can imitate part of the same shape, so the interpretation must include both stars and gas. Light from an active galactic nucleus creates another source of confusion. An active nucleus is a compact region where matter releases energy while falling toward a central black hole. It can produce a bright continuum and strong emission lines while occupying an area too small for Webb to resolve clearly at great distance. If all of this light is assigned to stars, the host galaxy appears too massive. Studies that model compact nuclear emission separately find that some initially extreme galaxies have more ordinary stellar masses, easing the strongest conflict with expected halo growth. Measurements across more wavelength ranges improve the estimate. Near-infrared data mainly sample ultraviolet and optical light, as it leaves a highly redshifted galaxy. Longer wavelength observations probe redder rest frame light, which is less dominated by the youngest massive stars, and can better trace accumulated stellar mass. Spectra measure line strengths and continuum shape, while high-resolution images test whether the light is extended across a galaxy or concentrated in a nearly unresolved center. Even with these methods, stellar mass remains an inference built from assumptions. Researchers report probability ranges and test different star formation histories, dust laws, chemical abundances, stellar distributions, and nuclear contributions. Some early galaxies remain genuinely massive after these tests, while others move downward substantially. Current evidence indicates that the most severe initial claims of impossible mass often weaken under improved analysis, although an excess of rapidly assembled massive systems may remain. The careful result is therefore narrower than the first impression. Webb detects light that can be produced by several mixtures of stars' gas dust and compact nuclear activity. Converting that light into mass requires a physical model, and the youngest cosmic environments are where those models are least tested. The galaxies do not arrive with ages stamped into their spectra. Their inferred masses become reliable only as separate sources of light are identified and allowed histories are compared. At this inner level of the measurement, apparent maturity can shrink without changing the redshift or the cosmic clock that places the galaxy in time. In Webb's deepest images, the earliest galaxies do not appear as grand spirals with wide arms or as smooth elliptical systems containing billions of old stars. Most occupy only a small number of resolution elements, and many look like compact patches, narrow streaks, flattened ovals, or irregular groups of bright knots. Their visible structure is simple in outline but difficult to interpret. A faint shape on the detector represents light from young stars glowing gas, and perhaps a compact nucleus all blurred by distance and by the optical response of the telescope. The study of a galaxy's form is called morphology. Morphology describes the distribution of light across a galaxy, including its size, elongation, concentration, symmetry, and internal clumps. In nearby space, detailed shapes often correspond to familiar categories such as spiral disks, rounded elliptical galaxies, and disturbed merging systems. At extreme redshift, these categories become less secure. Webb observes young structures at shorter stages of development, and the recorded ultraviolet light emphasizes active star-forming regions, rather than the full distribution of older stars. A galaxy that appears compact may be physically small, or its faint outer regions may fall below the detection limit. Surface brightness measures how much light arrives from each apparent area. Cosmic expansion strongly reduces the observed surface brightness of remote objects. A bright central region can remain detectable, while a broad dim envelope disappears into background noise. The measured radius then describes the visible portion, rather than every star belonging to the system. Webb's sharp infrared vision improves this measurement, but the earliest galaxies remain extremely small on the sky. Astronomers model the point spread function, the slight pattern created when the telescope records a point source. They compare this pattern with the observed galaxy. A source broader than the point spread function is spatially resolved, while a matching source may be too compact for its shape to be measured reliably. Small uncertainties in focus detector sampling or background subtraction can alter the inferred dimensions. Some confirmed galaxies within the first few 100 million years are clearly extended. Their light spans hundreds or more than 1,000 light-years, showing that star formation is distributed across a region rather than confined to one unresolved point. Even these systems remain much smaller than the broad stellar disks common in the present universe. High gas density allows intense activity to occur within compact volumes, producing bright ultraviolet emission from a limited physical area. Many early galaxies appear elongated. An elongated image can represent a thin disk viewed from the side, a thicker oval system, a cigar-shaped stellar distribution, or several clumps aligned within one forming galaxy. A two-dimensional image cannot by itself reveal the full three-dimensional form. Researchers therefore study the range of apparent axis ratios across many objects. The axis ratio compares the shorter visible dimension with the longer one. If a population consists mainly of circular disks seen at random angles, it produces a predictable mixture of round, face-on images and narrow edge-on images. Webb surveys find that a large fraction of young galaxies appear flattened in 2 dimensions, and many are more elongated than common nearby galaxies. Statistical modeling suggests that some may have oblong or tube-like 3-dimensional forms, rather than simple circular disks. Such shapes can arise when stars form along narrow gas structures, when small systems merge, or when gravity has not yet settled their motions into stable symmetry. The exact balance between disks and elongated bodies remains uncertain, because faint sources provide limited structural detail. Flattening does not automatically mean ordered rotation. A disk is often associated with stars and gas moving around a shared center, but a flat appearance alone measures geometry, not motion. A young galaxy can look disk-like while its material moves turbulently in several directions. Spectral measurements across different parts of a resolved source are needed to distinguish rotation from random motion inflow or merging. For the faintest and most distant galaxies, such spatially resolved spectra remain difficult. Irregular shapes are also common. Some galaxies contain 2 or more luminous knots separated by darker gaps. These knots may be giant star-forming regions within one shared gas system. They may also be distinct small galaxies approaching one another. Gravity brings early halos together frequently because cosmic structure is still assembling. When 2 systems interact, their stars and gas can form asymmetrical extensions, displaced centers or compressed regions of new star formation. Limited resolution can blend these features into a single uneven patch. Gravitational lensing sometimes reveals finer structure. A foreground cluster stretches and magnifies the image of a background galaxy. The distortion complicates the original shape, but a well-constrained lens model can reconstruct the source at a finer physical scale than Webb reaches without magnification. Strongly lensed systems show compact star clusters embedded within diffuse light and arranged across young galaxies. These clusters indicate that early stellar growth can proceed through multiple concentrated sites rather than through a smooth uniform sheet. The apparent form also changes with wavelength. Rest frame ultraviolet light traces hot stars that live briefly and remain near their birth clouds. Rest frame optical light includes a broader range of stellar ages and more closely follows accumulated stellar mass. Webb's different filters sample these regions after redshift moves them into the infrared. A galaxy can look clumpy in ultraviolet light, but smoother at longer wavelengths. Structural comparisons therefore require filters that correspond to similar emitted wavelengths at different redshifts. Dust adds further unevenness by blocking light along selected lines of sight. A dark lane can divide a bright region, while clear openings allow ultraviolet radiation to escape. Strong gas emission can make individual knots unusually prominent inside one filter. A central feeding black hole can create a point-like core that raises the measured concentration. Morphology must therefore be examined together with color and spectroscopy, so that shape is not assigned entirely to stars when other components contribute. Despite these limitations, Webb establishes that early galaxies possess more structural diversity than a picture of featureless newborn objects suggests. Compact systems coexist with flattened, elongated, clumpy and disturbed forms. Some show signs consistent with disks, while others appear dominated by irregular assembly. The range reflects differences in gas supply halo shape, viewing angle interactions, and the brief luminous phases selected by observation. Within these first systems, form is not a finished architectural state. It is the visible arrangement of matter, while galaxies are still gathering, compressing, and reorganizing under gravity. Inside the earliest galaxies, stars appear to grow with unusual speed because several processes operate together in a young and compact environment. Gas is abundant, dark matter halos are still assembling, and the first stellar populations produce intense ultraviolet light. Webb records this light after cosmic expansion stretches it into the infrared. The brightness suggests that some galaxies convert gas into stars rapidly, but the interpretation depends on how long the activity lasts, how massive the stars become, and how much of their light escapes. Star formation begins when gas becomes dense enough for gravity to overcome internal pressure. In the early universe, gas flows along the filaments of the cosmic web and falls into dark matter halos. These flows can deliver fresh material directly towards central regions. Collisions between streams remove part of their motion and compress the gas. As density rises, cooling allows the clouds to contract further. The process creates compact sites where many stars form within a short interval. The rate of star formation describes how much gas becomes stars during a given span of time. In nearby galaxies, the rate often changes gradually, though local star-forming clouds remain uneven. In very young galaxies, the rate can rise sharply. A small system may form a large fraction of its visible stars during a burst lasting only a few million or tens of millions of years. Such a burst is brief compared with cosmic history, yet it is long enough to fill a galaxy with hot, luminous stars. These hot stars dominate ultraviolet light. They are far brighter than low-mass stars of the same age, but they survive for much shorter periods. A galaxy observed during the peak of a burst therefore appears exceptionally luminous for its stellar mass. Once the most massive stars die, ultraviolet brightness falls rapidly, even if the total stellar mass changes little. Webb surveys are more likely to detect galaxies during the bright phase, producing a sample weighted towards systems caught at moments of intense activity. This selection effect is important. A population of small galaxies may spend much of its time in faint states, interrupted by short luminous episodes. Deep observations detect the episodes more easily than the quiet intervals. The resulting abundance of bright objects can appear larger than predictions based on steady star formation. Models that include variable or bursty activity often produce more luminous early galaxies without requiring a larger cosmic age. Gas conversion efficiency also shapes the result. This efficiency is the fraction of available gas that becomes stars before heating radiation or motion prevents further collapse. Early models often assume that low-mass galaxies convert gas inefficiently because young stars disrupt their surroundings. Webb observations suggest that some systems may reach higher efficiency for short periods. Dense gas, strong inflow, and compact geometry allow collapse to proceed quickly before feedback clears the region. Feedback begins almost as soon as massive stars form. Their ultraviolet radiation heats and ionizes nearby gas. Stellar winds push material outward. After a few million years, the most massive stars end their lives and release additional energy. These effects reduce the density of the surrounding clouds and can interrupt star formation. In a shallow gravitational well, part of the gas may escape the galaxy. In a more massive halo, heated gas may remain bound and later cool again. The competition between inflow and feedback produces cycles. Gas arrives, cools, and forms stars. Radiation and explosions then disperse or heat the clouds. New inflow restores the supply, and another burst begins. This cycle creates large changes in brightness over short intervals. Two galaxies with similar dark matter masses can look very different if one is near the peak of a burst and the other lies between episodes. The chemical simplicity of early gas also affects stellar output. Gas with few heavy elements loses heat differently from enriched gas. Stars formed from this material tend to be hotter at a given mass and emit more ultraviolet radiation. Their light makes a young galaxy appear more productive than a later galaxy, forming the same total mass of stars. The exact effect depends on the distribution of stellar masses and on how rapidly heavy elements spread through the system. The initial mass function remains a major uncertainty. If early clouds form a larger proportion of massive stars, ultraviolet luminosity rises strongly without a matching increase in total stellar mass. Such a distribution may occur in warm metal-poor gas, though observations do not yet establish one universal early pattern. Models test several possibilities because a modest change in the number of massive stars alters the inferred star formation rate and the amount of ionizing radiation. Compactness strengthens the intensity of these processes. Early galaxies often place star-forming regions within a small physical volume. High gas surface density supports rapid collapse and frequent cloud interactions. Radiation pressure and stellar winds also become concentrated, making feedback powerful. The same compact environment can therefore promote fast growth and bring that growth to a temporary halt. The duration of activity limits how much mass can accumulate. A galaxy shining brightly for 10 million years does not build the same stellar mass as one sustaining the same rate for 100 million years. Observed ultraviolet light mainly traces recent activity, so a high present rate does not prove that the galaxy has formed stars continuously since an extremely early time. Spectral modeling must distinguish a short burst from a long history of steady formation. Some galaxies show evidence for several stellar ages, indicating that activity begins, weakens, and resumes. Others are consistent with a dominant young population. The available spectra remain faint, and age estimates overlap with uncertainties in dust metallicity, gas emission, and stellar evolution. The secure conclusion is that rapid star formation occurs in at least part of the early galaxy population. The exact duration and average efficiency vary from system to system. Within these young structures, fast stellar growth does not require additional billions of years. Dense inflow compact clouds, hot metal, poor stars, and brief observation-favoured bursts can create strong luminosity within a limited cosmic interval. Webb reveals that the conversion from gas to visible starlight may proceed more quickly and less steadily than many earlier models assume. The unusual brightness therefore reflects the pace and rhythm of early star formation measured during short luminous phases inside galaxies that are still assembling. Within the earliest galaxies, stars do not form in isolation. They emerge from gas-return material to that gas and gradually change its chemical character. Webb studies this cycle through faint continua bright emission lines and the way dust alters the passage of light. These signals reveal that some galaxies become chemically active within only a few 100 million years, while the degree of enrichment differs sharply from one system to another. The first ordinary matter consists mainly of hydrogen and helium with only traces of lithium. Elements such as carbon, oxygen, nitrogen, silicon, and iron do not appear in significant amounts until stars create them. Nuclear reactions inside stars build heavier nuclei from lighter ones. When stars lose outer layers or end their lives, part of this material enters the surrounding gas. Each generation therefore changes the raw material available to the next. Astronomers describe the abundance of elements heavier than helium as metallicity. The term does not mean that every such element behaves like a metal in ordinary chemistry. It serves as a compact measure of chemical enrichment. A galaxy with low metallicity contains gas that has experienced relatively little stellar processing. A more enriched galaxy contains material that has passed through stars and returned carrying newly formed elements. Webb detects chemical enrichment mainly through spectroscopy. Ionized gas around hot young stars produces emission lines at specific wavelengths. Oxygen, carbon, neon nitrogen, sulfur, and hydrogen can each leave characteristic features. Cosmic expansion shifts these lines into the infrared. Their relative strengths depend on abundance, gas temperature, density, and the hardness of the radiation field. A strong oxygen line confirms that earlier stars already synthesize and disperse oxygen before the observed light begins its journey. Hydrogen lines provide a reference because hydrogen remains the dominant element. By comparing oxygen or carbon features with hydrogen features, researchers estimate chemical abundance. The method requires physical models of glowing gas. A line may strengthen because an element is more abundant, but it may also strengthen because the gas is hotter, or because the ionizing stars produce more energetic photons. Several line ratios are therefore considered together when the data allow it. Some very distant galaxies show clear oxygen emission despite their young cosmic age. This evidence means that star formation begins early enough for massive stars to manufacture heavy elements, die, and enrich nearby gas. Massive stars complete this cycle quickly because their lifetimes can be only a few million years. Significant oxygen does not require billions of years. A compact galaxy experiencing repeated bursts can become measurably enriched within a relatively short interval. Carbon and nitrogen provide different timing information because they can arise through several stellar pathways. Massive stars contribute part of their production, while lower mass stars release additional amounts over longer periods. Unusual carbon or nitrogen ratios can therefore reflect stellar masses rotation gas flows, or the timing of enrichment. Current measurements reveal diverse chemical conditions, but many spectra remain too faint to determine a complete abundance pattern. The gas itself is often highly ionized. Intense ultraviolet radiation from young metal-poor stars removes electrons from atoms and creates energetic nebulae. A nebula is a cloud of gas that emits light after absorbing energy. Early galaxies can contain emission lines stronger than those typical of nearby systems. Their gas may have high-density, strong radiation fields and relatively little dust. These conditions change the relationship between observed line strength and total stellar mass. Gas does not remain evenly distributed. Gravity draws it toward dense centers and clumps, while radiation winds and stellar explosions push some of it outward. Fresh gas from the cosmic web can enter with lower metallicity and dilute enriched regions. Outflows can carry heavy elements into surrounding space. The measured spectrum therefore represents a mixture of inflow, local star formation, recycled material, and escaping gas. Dust forms from solid particles containing elements such as carbon, oxygen, silicon, magnesium, and iron. It requires earlier stellar processing because the first hydrogen and helium gas cannot produce ordinary cosmic dust by itself. Massive stellar explosions can create grains rapidly, while winds from evolved stars add further material when enough time passes. Some newly formed grains are destroyed by shocks, so the amount that survives depends on the balance between production, growth, and destruction. Even a small amount of dust changes a galaxy's appearance. Dust absorbs ultraviolet and visible light, especially at shorter wavelengths, and converts part of the energy into heat. The warmed grains then emit infrared radiation. A dusty galaxy can appear faint in ultraviolet observations even while forming stars rapidly. A nearly dust-free galaxy allows more ultraviolet light to escape and may appear unusually bright for the same underlying rate of star formation. At extreme redshift, dust measurements are difficult. Webb observes the shorter emitted wavelengths after they are stretched into the infrared, but much of the thermal glow from cool dust shifts to even longer wavelengths. Radio and sub-millimeter observatories can search for that emission, though sensitivity and atmospheric limitations restrict the faintest targets. Researchers also infer dust from the slope of ultraviolet light and from the relative strength of hydrogen lines. Each method depends on assumptions about geometry and temperature. Some early galaxies show red colors that may indicate dust, yet the same colors can arise from older stars or strong gas emission. Others appear remarkably blue, consistent with young populations and little obscuration. A single dust law does not describe every system. Grain size composition and distribution may differ from those in the Milky Way, because the sources and processing history are different. Chemical enrichment and dust formation therefore proceed unevenly. Dense galaxies with repeated stellar activity can develop measurable oxygen and obscuring material early, while smaller or newly forming systems remain close to pristine conditions. The evidence does not show fully mature chemistry across the young universe. It shows a patchwork in which stellar products accumulate locally, mix imperfectly, and sometimes escape. Inside this chemical layer, Webb finds rapid change rather than impossible age. Heavy elements can appear soon because massive stars evolve quickly, and dust can begin forming after only a few stellar generations. The precise abundances remain uncertain when line measurements are weak or model-dependent, but the general process is clear. Early galaxies are already transforming simple primordial gas into a more complex medium. One burst of star formation and one cycle of stellar return at a time. At the centers of some young galaxies, gravity gathers matter into regions smaller than the galaxies themselves. Gas dust and stars move through a deep gravitational field created by a black hole. The black hole emits no light from within its event horizon, the boundary beyond which nothing returns. The surrounding material can shine before crossing that boundary. As gas falls inward, friction and magnetic forces convert orbital energy into heat. The resulting glow can rival or exceed the combined light of the surrounding stars. This luminous central region is called an active galactic nucleus. Its appearance depends on the rate of infall, the mass of the black hole, and the amount of obscuring material along the line of sight. Hot gas near the center produces ultraviolet and visible light, while surrounding dust absorbs part of that energy and releases it again in the infrared. At great redshift, cosmic expansion moves these wavelengths into Webb's observing range. A compact early galaxy can therefore appear unusually bright even when much of the detected radiation comes from accretion rather than from stars. Spectroscopy provides the main evidence for this activity. Gas moving close to a black hole can travel at thousands of kilometers per second. Its rapid motion broadens the emission lines produced by hydrogen and other elements. Instead of forming a narrow peak at a wavelength, the line spreads across a wider range because gas on different sides of the center moves toward and away from the observer. Broad lines are a common sign of an active nucleus, although dense stellar environments and powerful outflows must also be considered. Narrower lines reveal highly ionized atoms that require energetic radiation. Ordinary young stars can produce strong ultraviolet light, but some ions need photons more energetic than most stellar populations provide. A combination of broad hydrogen emission, high ionization features compact structure, and a bright continuum strengthens the black hole interpretation. No single feature always settles the issue, especially when spectra contain few photons. Researchers compare several indicators and test whether a stellar model can reproduce the same signal. Webb identifies active black holes in galaxies observed within the first billion years. Some occupy systems that previously appear to be dominated by star formation. Detailed spectra show that their central sources contribute part of the total luminosity. In GNZ 11, a galaxy seen when the universe is only a few 100 million years old, the spectral evidence supports a rapidly feeding black hole. Its activity offers a natural explanation for part of the galaxy's exceptional brightness, without requiring every photon to come from a vast stellar population. A wider mystery appears in the compact objects known as little red dots. These sources are small on the sky, common during early cosmic history, and unusually red at longer infrared wavelengths while often retaining blue ultraviolet light. Many show broad hydrogen lines consistent with accreting black holes. Their red color may arise from dust-dense gas or the reprocessing of radiation around a buried central source. Some may contain vigorous star formation as well. The population is not yet explained by a simple model. The abundance of these objects suggests that black hole growth may be common in young galaxies. Webb detects active nuclei that are less luminous than the bright quasars found in earlier surveys. Quasars represent the most radiant accreting black holes and are visible across enormous distances, but they sample only the brightest end of the population. Webb reaches fainter systems, revealing a broader range of growth rates and host galaxy masses. A black hole grows when it captures gas or merges with another black hole. The initial object is called a seed. One pathway begins with the remnants of the first massive stars. These seeds may contain tens or hundreds of solar masses. Another pathway involves the rapid collapse of a large gas cloud, potentially producing a seed with thousands or more solar masses. Dense stellar clusters may provide additional routes through repeated collisions and mergers. Evidence does not yet establish one origin for every early massive black hole. Growth through gas accretion faces a natural limit. Radiation from hot infalling material pushes outward against the gas that continues moving inward. The balance between radiation pressure and gravity defines the Eddington limit. A black hole feeding near this limit grows exponentially if a steady fuel supply remains available. Small seeds need long periods of nearly continuous accretion to become millions or billions of times the mass of the Sun within the first billion years. Interruptions make the timing more difficult. Accretion can exceed the conventional limit for limited periods when dense flows trap radiation or carry energy inward. Such super Eddington episodes allow faster growth, though their duration and efficiency remain uncertain. A black hole may also pass through quiet phases after consuming or expelling nearby gas. Webb has found evidence for early black holes with low, present accretion rates, suggesting that rapid earlier growth may be followed by dormancy. Observations capture one phase rather than the complete history. The relation between black hole mass and host galaxy mass appears different in some young systems. Several early black holes seem unusually massive compared with their visible stellar populations. Selection contributes to this pattern because luminous active nuclei are easier to detect than inactive black holes of the same mass. Stellar masses may also be underestimated when the nucleus overwhelms faint host light. Even after these effects are considered, some systems may indicate that black holes and galaxies do not always grow in the balanced proportion seen nearby. Central activity also changes the host. Radiation heat surrounding gas winds carry material outward, and jets may transfer energy into larger regions. This feedback can reduce star formation by removing or heating fuel. It can also compress gas, and briefly encourage new stars along dense boundaries. In small early galaxies, the shallow gravitational field makes the outcome especially sensitive to the strength and direction of the outflow. The black hole layer therefore alters the interpretation of Webb's brightest early sources. A compact point of light can contain young stars, ionized gas-hot dust, and an active nucleus at the same time. Assigning all of its brightness to stars produces excessive stellar masses and apparent ages. Separating the central component often reduces the tension with galaxy formation models. The remaining evidence still shows rapid black hole growth under early conditions that are not fully understood. It does not show that the universe must be older. It shows that dark central objects can become influential, while their host galaxies are still young, small, and chemically developing. A redshift measurement begins with light, but cosmic age begins with a model of expansion. Webb records how much a galaxy's wavelengths have been stretched since the light leaves the source. That stretching can be measured directly from a spectral break or from known emission lines. The number itself does not state how many years have passed. To turn redshift into an age, cosmologists calculate how quickly space expands at different stages, and how that rate changes as the contents of the universe become more or less important. The starting quantity is the scale factor, a simple description of the relative size of the universe at different times. In the present era, the scale factor is assigned a value of 1. At earlier times, it is smaller. Redshift is directly connected to this factor because wavelengths stretch with expanding space. A high redshift therefore corresponds to a much smaller scale factor and to an earlier epoch. The connection between scale factor and time, however, depends on the expansion history. Expansion is governed by the average energy and matter content of the cosmos. Radiation contributes strongly at the earliest times because its energy density falls rapidly as space expands. Matter later becomes dominant because its density decreases more slowly. Dark energy becomes important much later because its density remains approximately constant in the Standard Model. The changing balance among these components determines whether expansion slows or accelerates, and therefore determines how much cosmic time corresponds to a given redshift. Ordinary matter and dark matter both contribute gravity. Ordinary matter interacts with light and forms atoms, gas stars, and planets. Dark matter remains invisible except through gravity, but it accounts for most of the matter density. In calculations of the large-scale expansion, the two forms of matter influence the overall rate in similar gravitational ways. Their combined density is one of the central quantities used when redshift is converted into a look-back time. Dark energy affects the later history differently. Observations of distant supernovae, the cosmic microwave background, and the large-scale distribution of galaxies indicate that expansion accelerates at relatively recent cosmic times. In the Standard Model, this acceleration is represented by a cosmological constant, a form of energy associated with empty space. Its physical nature remains uncertain, but its measured effect on expansion can be included in the calculation. The present expansion rate is described by the Hubble constant. It gives the approximate rate at which separation increases with distance in the nearby universe after local gravitational motions are averaged out. Different methods produce values that do not agree perfectly. Measurements based on the early universe and the Standard Model tend to give a lower value than several measurements based on nearby stars and supernovae. This disagreement is known as the Hubble tension. The tension affects detailed calculations, but it does not automatically change the age of the universe by several billion years. A cosmological model must satisfy several observations at once. Changing the present expansion rate also changes the inferred matter, density, distance scale, and development of structure. A model with a different Hubble constant cannot be judged by one number alone. It must continue to reproduce the microwave background galaxy, clustering supernova distances and other measurements. For very high redshift galaxies, most of the light travel time occurs during epochs when matter dominates the expansion. Dark energy has little direct influence there because its relative contribution is small. Even so, the present-day parameters are part of the model used to connect the early era with the present. Once these parameters are chosen, the redshift can be mapped to the age of the universe when the photon is emitted. The calculation produces two related times. Look-back time measures how long ago the observed light was emitted. Cosmic age at emission measures how old the universe is at that moment. If the present age is about 13.8 billion years, and a galaxy's light has travelled for roughly 13.5 billion years, the galaxy is observed when the universe is only a few 100 million years old. These numbers are linked but not identical because expansion affects distance and timing. Distance also has several meanings. The distance that light travels is not the same as the galaxy's present separation from the observer. While the photon moves, space continues expanding. A galaxy whose light begins its journey more than 13 billion years ago can now be tens of billions of light years away in present moving distance. Cosmologists use different distance definitions for brightness, angular size, and large-scale maps, each suited to a specific measurement. The strength of the standard conversion comes from consistency. The same expansion history that assigns an age to a redshift must also explain the pattern of the cosmic microwave background, the acoustic scale seen in galaxy clustering, and the observed brightness of distant supernova. A large change to the cosmic age cannot be inserted independently. It changes several linked predictions at once. This is why an unexpectedly mature galaxy does not immediately imply that redshift has been translated into time incorrectly. The measured redshift can be secure while the inferred stellar age or mass remains uncertain. If a galaxy appears too developed for its assigned epoch, researchers first test the astrophysics that operates within the galaxy. They examine star formation history, dust gas emission, black hole activity, stellar populations, and lensing. Only if these explanations fail across a broad and reliable sample does the expansion model itself become a stronger target for revision. Alternative cosmologies can produce different redshift time relations. Some introduce evolving dark energy additional particle species, modified gravity, or changes to early expansion. Such models are scientifically testable because they alter more than galaxy ages. They change the predicted growth of structure, the microwave background lensing, and the relation between multiple distance indicators. Most remain constrained by the precision of existing data. Within this layer of the investigation, Webb provides the redshift, while cosmology provides the clock. The telescope measures how far light has been stretched and identifies the spectral features that establish the source's place in the expanding sequence. The age assigned to that source emerges from a framework tested across many independent observations. The conversion is therefore neither a direct reading from the detector nor a flexible guess. It is a calculated bridge between measured light and the changing expansion of the universe. Testing the standard cosmic model begins by separating different kinds of tension. Webb observes galaxies that are unexpectedly bright, massive-looking, chemically active or compact at very early times. These findings concern the speed with which structure becomes visible. They do not automatically measure the expansion rate, and they do not directly measure the total age of the universe. A galaxy formation problem and a cosmological expansion problem can exist at the same time without having the same cause. The standard framework is commonly called lambda cold dark matter. Lambda represents the cosmological constant associated with dark energy, while cold dark matter describes invisible matter moving slowly enough in the early universe to gather efficiently under gravity. Ordinary matter radiation and a nearly flat large-scale geometry complete the basic picture. With a small set of parameters, this framework explains the cosmic microwave background, the large-scale distribution of galaxies, gravitational lensing light element abundances, and much of the observed expansion history. Within this model, early galaxies grow inside dark matter halos. Small density variations strengthen through gravity, halos merge, gas falls inward, and stars form. Before Webb, many simulations predict relatively few very bright galaxies during the first several 100 million years. Webb finds more luminous systems than some of those predictions. The first response is therefore to examine the connection between dark matter halos and emitted light rather than to change the entire expansion history. Several adjustments remain within ordinary galaxy physics. Star formation may be more efficient in dense early gas. Activity may occur in short bursts that make galaxies temporarily brighter. Metal-poor stars may produce more ultraviolet radiation for the same stellar mass. Dust may obscure less light than expected in some systems. Strong emission from ionized gas may raise the brightness measured through broad filters. Feeding black holes may contribute light previously assigned to stars. Each effect changes what a young halo looks like without requiring a different age for the cosmos. As spectroscopy improves, some of the strongest early claims become less extreme. Secure redshifts confirm that luminous galaxies truly exist at very early times, while improved models often reduce estimates of their stellar masses. This combination matters. The distance can remain extraordinary, while the apparent requirement for an enormous old stellar population weakens. A surprising galaxy then becomes a test of rapid formation rather than evidence that the cosmic timeline has failed. Simulations can also change without changing cosmology. Higher resolution allows researchers to follow smaller gas clouds and shorter bursts of star formation. More detailed feedback models alter how radiation, stellar winds, and explosions regulate gas. Different assumptions about stellar birth masses change the amount of ultraviolet light produced. These refinements can increase the predicted number of bright early galaxies while preserving the same dark matter distribution and expansion history. A deeper revision becomes necessary only if reasonable astrophysical changes fail across a large reliable sample. Cosmological parameters influence how quickly dark matter structure appears. Increasing the amount of early structure could provide more halos in which galaxies form. Changing the properties of dark matter could alter the growth of small systems. Additional early energy components could modify expansion before galaxies emerge. Any such change, however, also affects measurements far outside Webb's galaxy surveys. The cosmic microwave background is especially restrictive. Its temperature and polarization patterns measure conditions when the universe is about 380,000 years old. A model that changes early expansion must still reproduce those patterns with high precision. It must also remain consistent with the abundance of light elements created during the first minutes, the later distribution of galaxies, and the bending of light by large-scale matter. A proposed solution to one-Webb tension cannot be judged only by its success with early galaxies. The Hubble tension is a separate issue. Measurements based on nearby Cepheid variable stars and Type I supernovae produce a present expansion rate higher than the rate inferred from the cosmic microwave background under the Standard Model. Webb examines Cepheids in infrared light with sharper resolution than Hubble, reducing the possibility that unresolved neighboring stars create a large systematic error. These observations broadly support the earlier local measurements, so the disagreement remains. This persistence is important for cosmology, but it does not mean that Webb's earliest galaxies and the Hubble tension are one discovery. The galaxy tension concerns how quickly luminous structure develops at high redshift. The Hubble tension concerns a disagreement between methods that infer the present expansion rate. A new physical model might eventually influence both, but current evidence does not establish a common explanation. Researchers test possibilities such as additional energy in the early universe, extraparticle species, modified gravity, or dark energy that changes with time. Each proposal shifts several observables together. Early dark energy, for example, can alter the scale used to infer the Hubble constant from the microwave background. It can also change structure growth. The permitted amount is tightly constrained, and no version has yet replaced the Standard Model with broad agreement across all major datasets. Large galaxy surveys add another layer. Measurements of baryon acoustic oscillations trace a preferred scale left by sound waves in the early plasma. Combined with supernova observations and the microwave background, recent results show hints that dark energy may not remain perfectly constant. The statistical significance depends on which datasets are combined, and the evidence has not reached the level required for a discovery. The cosmological constant therefore remains the standard description while further measurements continue. The age of the universe is similarly resistant to isolated changes. A different expansion history can shift the calculated age, but it must fit the same network of observations. Stellar ages, the microwave background galaxy clustering, supernova distances, and other measurements constrain the permitted range. Current data do not support adding billions of years simply to provide early galaxies with more time. At this level, Webb acts as a stress test rather than a replacement for cosmology. Its observations expose parts of early galaxy formation that simplified models underestimate. They also strengthen independent measurements relevant to the expansion rate disagreement. Both results encourage more precise physics and more careful cross-checking. The Standard Model remains remarkably successful across cosmic scales, while specific tensions show where its assumptions and the astrophysics built upon it require the closest examination. At the deepest level of the evidence, the question is no longer whether Webb finds something unexpected. It does. The central issue is what kind of expectation fails. The most secure observations show that luminous galaxies, chemically enriched gas compact stellar systems, and actively feeding black holes exist earlier than many models predict. These findings force revisions to the pace of early structure formation. They do not currently require a revision of the measured age of the universe. The age near 13.8 billion years remains supported by several independent observations that describe the expansion of the cosmos as a whole. The cosmic microwave background provides a precise record of the young universe. Baryon acoustic oscillations preserve a large-scale distance pattern created by sound waves in early matter and radiation. Supernovae trace how expansion changes at later times. The abundance of light elements constrains the hot conditions of the first minutes. Stellar populations provide additional lower limits because the universe must be older than its oldest stars. These methods do not all depend on the same instruments or the same physical processes. Their agreement is therefore important. A systematic error in one technique does not automatically reproduce the same cosmic history in the others. The standard cosmological model combines these measurements into a coherent expansion timeline in which the present age remains close to 13.8 billion years. Small adjustments to cosmological parameters can move the results slightly, but current evidence does not support an increase large enough to solve early galaxy tensions simply by adding billions of years. Webb contributes to this picture in a different way. It observes individual objects within the established expansion history. Its most distant confirmed galaxies appear only a few 100 million years after the hot beginning. Their redshifts come from the stretching of spectral features, while their stellar masses, ages, dust content, and star formation histories depend more heavily on physical models. The redshift is often more secure than the interpretation of the internal stellar population. This difference explains why early claims can appear more dramatic than later conclusions. A newly detected red source may initially receive an extreme stellar mass based on broadband colors. Deeper spectroscopy can reveal strong gas emission a younger stellar population, or light from an active black hole. The estimated mass then falls while the redshift remains high. The galaxy is still genuinely early and still scientifically important, but the need for an impossible amount of prior growth becomes weaker. Some tension remains even after these corrections. Bright galaxies appear abundant at high redshift, and several systems form stars efficiently enough to challenge older prescriptions. Early black holes also appear capable of rapid growth. Chemical enrichment proceeds quickly in some regions. These findings indicate that the first few 100 million years are more productive and more varied than simplified models suggest. The uncertainty now concerns how matter organizes and converts into light under those conditions. A mature-looking galaxy is not necessarily an old galaxy. A compact burst of star formation can generate intense ultraviolet luminosity in a short time. Massive stars can create oxygen after only a few million years. Stellar explosions can distribute heavy elements rapidly. Dense gas can produce repeated generations without requiring a long cosmic interval. A feeding black hole can add central brightness that resembles a larger stellar population. Each process compresses visible development into shorter periods. The phrase older universe therefore describes only one possible class of explanation, and current measurements do not favor it as the necessary one. A different age requires a different expansion history. That revised history must reproduce the microwave background, large-scale structure, supernova distances lensing, light element abundances and local measurements at the same time. No broadly accepted alternative presently does this, while clearly outperforming the standard model. The Hubble tension remains an important unresolved problem. Local distance measurements and early universe inferences still disagree about the present expansion rate. Webb strengthens confidence in parts of the local distance ladder by resolving crowded stellar fields more clearly, but this does not directly show that the universe has a different age. Expansion rate cosmic composition and age are connected through the full cosmological model rather than through one local measurement. Other tensions also receive careful attention. Some large-scale surveys allow the possibility that dark energy may evolve rather than remain perfectly constant, depending on the combination of datasets and assumptions. Such results undergo tests against larger samples and improved calibrations. Even if future evidence requires a modification to dark energy, the resulting change in cosmic age must still come from the complete expansion history. It cannot come from early galaxy brightness alone. The scientific value of Webb lies partly in this separation of questions. It reaches far enough back to expose weaknesses in models that rely on limited data. It measures populations that earlier telescopes only hint at. As the sample grows, extreme objects become part of a statistical distribution rather than isolated curiosities. Spectra replace uncertain colors, and direct emission features replace some model-dependent estimates. The early universe becomes less mysterious in some respects and more demanding in others. The most careful conclusion is therefore narrower than the project title suggests. Webb does not measure a universe older than 13.8 billion years. It reveals that important structures become luminous, earlier grow faster, and develop more complex internal conditions than many pre-Webb calculations predict. The difference matters because galaxy formation models must now explain this efficiency without violating the larger body of cosmological evidence. At the innermost foundation of the question, the apparent contradiction becomes a distinction between cosmic age and cosmic development. The clock still points to approximately 13.8 billion years under the best supported model. What changes is the understanding of how quickly matter begins to organize after the hot beginning. Webb's strange result is not an older cosmos revealed directly in infrared light. It is a young cosmos proving more capable of rapid structure chemistry and luminous growth than many earlier models allow. Across the observable universe, ancient light continues to arrive from distances shaped by expansion and time. The cosmic microwave background remains as a faint record of the early hot state, while distant galaxies preserve later moments when stars, gas dust, and black holes begin forming recognizable structures. Each layer carries a different kind of information, and together they build a consistent history rather than a single measurement of cosmic age. Webb extends this history into periods that were once almost inaccessible. Its infrared instruments reveal galaxies shining within only a few 100 million years of the beginning. Some are brighter, more chemically enriched, and more active than earlier calculations expect. Their existence changes the understanding of how quickly ordinary matter can gather cool-form stars and feed central black holes. The measurements also become quieter when examined carefully. Brightness does not always mean enormous mass. Red color does not always mean great stellar age. Strong emission can come from ionized gas dust, young stars, or active black holes. Improved spectra gradually separate these components and reduce some of the most extreme early interpretations. The larger cosmological framework remains supported by the microwave background galaxy, clustering supernova observations and other independent evidence. Within that framework, the universe remains approximately 13.8 billion years old. Uncertainties continue and some tensions remain unresolved, but no confirmed. Webb result currently requires several additional billions of years. The deeper change lies in the pace of development. The early cosmos appears capable of building luminous structure with remarkable efficiency. gas gathers, stars ignite, heavy elements spread, and black holes grow while the universe is still young. Webb brings these processes into clearer view, leaving the cosmic clock largely unchanged, while making the first chapters of visible structure richer, faster, and more detailed than before.